Okay, welcome everybody to our Computer Science Alumni and Friends Virtual Public Lecture Series, number 2. And our guest today is Dr. Larry Matthies, who's an alumnus of the Computer Science Department from 1979. And he attended Campion. So just a note to people, if you can turn off your cameras, participants, if you can turn off your cameras just to keep the internet connection working well for us. And then we can rejoin at the end for questions. So first of all, a warm virtual welcome to members and friends of the University of Regina and its 3 federated colleges, the First Nations University of Canada, Campion College, and Luther College. The University of Regina is situated on Treaty 4 lands with a presence on Treaty 6 lands. These are the territories of the Cree, Saulteaux, Dakota, Lakota, and Nakota, and the homeland of the Métis-Michif Nation. Today, these lands continue to be the shared territory of many diverse peoples from near and far. So this event is hosted by the Department of Computer Science. And just a quick note of history. The final approval to create the Department of Computer Science was granted in November 1968. Some of the first graduates of the program convocated in 1974 as the University of Saskatchewan Regina campus became the University of Regina. And Larry Symes, an alumnus of the Regina campus, was the first department head. So this is the second event in our virtual public lecture series, and we're looking forward to the next one in the series in spring 2021. We welcome your feedback and suggestions. Please send them along to Daryl Hepting, that's me. There's my email address, daryl.hepting@uregina.ca. So I'm a professor in the Department of Computer Science and an alumnus. Now to give a brief introduction to our guest, Dr. Larry Matthies. After his studies here concluded in 1979, he went to the University of Waterloo for a master's degree and then a PhD from Carnegie Mellon University before joining the Jet Propulsion Lab at the California Institute of Technology in 1989, where his job allows him to personally participate in putting robots on other planets. He gave the 2004 Basterfield Lecture and the keynote at the 2013 AIGI CRV conference, both non-virtually, at the University of Regina. So without further ado, please help me welcome our speaker, Dr. Larry Matthies.
Thank you. It's a pleasure to be here. Thanks for the invitation, Daryl. I'm going to turn off my video for the presentation. It's a pleasure to see familiar names on the participant list. I can't say hello to everybody individually, so I'll just say a general hello. Nice to see you again virtually. The topic for today is robotic Mars exploration. As Daryl said, I work at the Jet Propulsion Lab, which is part of Caltech. Start with a few basic Mars facts and figures. Mars is about half the diameter of Earth, about twice that of the moon. It's 1.5 times as far from the sun as Earth, has about 1/3 of the gravity. We'll be talking a little bit about the Mars helicopter today, so it's worth noting that the density of the Mars atmosphere is only about 1% of the atmosphere on Earth. It has very cold nights, but daytime, summer high at noon on the equator is fairly comfortable, 27 degrees Celsius. It's kind of convenient that the length of a Mars day is just a little bit longer than a length of an Earth day. So when we're doing operations, that's a useful unit to keep track of. So why do we explore Mars? NASA has essentially a standard rationale for Mars, which is these 4 topics on the left. Look for life, understand climate, explore its geology, prepare for eventual human exploration, water plays a central role in all four of those things. There's been a lot of water on Mars over its history. You can see in the image that's up now, there is a water ice cap on both poles. A lot of carbon dioxide also condenses in the winter hemisphere. We can see from orbital imagery that deep in the past, there's been a lot of water on the surface, 3.5 to 4 billion years ago, and sporadically more recently than that. So this is a photo taken by the Viking orbiter that shows branching river valleys. Don't see this much branching in very many places, but nevertheless, we see a lot of evidence of liquid water on the surface of Mars. Let's see, I'm having trouble with, there we go. Slide wasn't advancing. So there are theories that there appear to have been a large liquid water ocean in the northern hemisphere, which is much lower than the southern hemisphere, sometime in the past, around 3.5 billion years ago. So where there's water, natural question, was there life? Or possibly, is there even life there today in some protected niche? So we've had a number of missions looking for, first of all, to understand the history of water on Mars. So for a number of years, NASA's theme for exploring Mars was follow the water. So this is a bit of a busy graphic, but it illustrates missions that were still operational at Mars in the time frame from 2001 to 2009. There's a bunch of orbiters, some rovers. And then on the right-hand side, it illustrates missions that have just arrived in the last month in February, and missions that are planned going forward in the next decade. So we had the rovers Spirit and Opportunity back in 2004 and years after that, following the water. We had the Phoenix lander. Those aren't shown here. Those basically taught us a lot about the history of water on Mars. Then we transitioned to a different theme, which was explore the habitability of Mars. So yes, there was water, but that's not all it takes for the conditions to be conducive for life. So the Curiosity rover that we launched in 2011, and it's still operating, its mission was to explore for habitability. And so it found evidence of ancient stream beds. And I'm not a geologist, so you'll have to excuse me if I don't get it exactly right, but it found clay minerals and basically evidence that that water had a neutral pH and that there were chemical processes going on that would supply energy to make life possible. So we concluded that indeed Mars was habitable somewhere 3.5 to 4 billion years ago. So then the question becomes, was it ever inhabited? Was there microbial life? Could there still be life there now? So that's the current theme, seek signs of life. That's the mission of Perseverance. So if you can see my cursor, we've got the Mars 2020 rover, that's Perseverance. I'll be talking more about how it's going to be searching for signs of life. That's the first step in what we hope will be a Mars sample return campaign. So a key part of the mission of Perseverance is to acquire 20 or 30 small samples of rock and leave them in caches on the ground for a later mission to come and pick those up. So that's the Mars Sample Return Lander. This is aspirational right now. We are working towards such a mission, but it's still early days. That's why we have this disclaimer at the bottom that says for planning and discussion purposes only. But the idea is we would launch a container up into Mars orbit. There would be another spacecraft called the Earth Return Orbiter that would rendezvous with the sample container in Mars orbit and bring it back to Earth. And so that whole campaign is a collaboration between NASA and the European Space Agency. As you probably know, other nations are also sending missions to Mars now. So European Space Agency has a rover in development called ExoMars. They're planning to launch that in 2022. It slipped a little bit from where we showed in this graphic. United Arab Emirates has an orbiter China has an orbiter there with the rover that I understand is going to land in May. And then there are other aspirations further in the future. So to give some idea of scale, these are the family photo basically of the rovers we've sent, that NASA has sent to Mars. So first we had Sojourner, launched in 1996. It was 11 kilograms. Then we had the two rovers, Spirit and Opportunity, launched in 2023. And then Perseverance and Curiosity are more or less carbon copies, about the same size. They have different instruments. So they're both operating on Mars now, about a metric ton. And they're the first ones we've sent that are powered by nuclear power. They have something we call a radioisotope thermal generator on the back. It's not installed here, but it goes on the back. And that's loaded with plutonium to generate heat. And then that heat is converted to electricity to power the rover. The rover also has rechargeable lithium-ion batteries, because the RTG only puts out about 110 watts. So we charge up the battery and run off the battery and the nuclear power during operations, and then overnight we can recharge the battery. So moving on, here's a quick illustration of a bunch of the cameras that are on the rover. So we use the cameras for navigation, and we use stereo pairs of cameras for 3D perception on the rover, which is very analogous to the way humans do 3D perception. So we have a pair of cameras we call the HAZ cams, for hazard cameras, mounted down low in the front. They're aimed down with a very wide field of view so they can see rocks in front of the rover. We have another pair of those in the back so that we can drive forward or backward. We have a pan tilt mast here. This can pan 360 degrees and tilt up and down, with some more stereo cameras on here for navigation. The mast cam Z is for science. That's a stereo pair of cameras with zoom capability, so they can take close-ups of objects a long way away. The thing called SuperCam is actually a science instrument. There's a laser in there that can zap rocks up to about 7 meters away, and then they will give off light that it can image in order to measure the or to infer the mineral content of rocks up to about 7 meters away. And then it's got a remote micro imager to be able to look at, I don't remember the resolution, but maybe 10 to 20 micron per pixel, to look at the mineralogy and texture of what's being observed there. There's this arm, which is for instruments and sampling. So I'm not going to go into a lot of detail here, but what we call Pixel is an X-ray lithography instrument. Anyway, it's to measure elemental composition of rocks. And then Sherlock is a Raman spectrometer. It's to measure organic molecules and minerals. And so organic molecules, of course, have carbon. That's an important part of the instrument suite to see if there could be any molecules indicative of prior life on Mars. And then there's also a core drill on this arm, and that's used to drill down into rock, get small cores of rock, and then it folds back into the body of the rover here. And we'll illustrate that in a movie in a little bit. This is another artist concept that focuses on the scientific instruments. I've already talked about several of these. There's also META is a weather station, measures temperature, atmospheric pressure, winds. RIMFAX is a ground penetrating radar that penetrates up to about 10 meters with a vertical resolution of about 30 centimeters to observe the subsurface structure and see what we can learn from that. And then MOXIE is actually a technology experiment for converting CO2 from the atmosphere into oxygen. And that's to prove out that technology for potential use in future human missions to Mars. So here is a movie. Let's hope it plays properly. Just illustrating how we operate the arm with the core drill on the arm to acquire samples. All that stuff on the end of the arm is about 45 kilograms, so it's a fairly heavy payload. So these cores, I've forgotten how long they are, but a few centimeters long. And these are to bring back to Earth. So what has to happen is they get put inside the body of the rover into aluminum cylinders. And those cylinders get hermetically sealed because we want to preserve the sample intact. We don't want, there's probably no gases in there, but we want to preserve the sample intact. And we're concerned about should there by some remote chance be actually any life still existing on Mars, we don't want any chance of that being released on Earth and causing trouble here. So these tubes are hermetically sealed to protect the sample and to protect Earth. And then they get stored in inside the vehicle like this. We've got capacity to acquire something like 40 of those and capacity to send about 30 of them back. And they're just going to be dropped by the rover somewhere on the ground. We call that the sample cache. And then the later mission will come and pick those up and put them on the rocket to send back to Earth. Now, where are we going with this? So Perseverance has landed in a crater called Jezero Crater. So what you see here is an elevation map. The scale bar shows you there 10 kilometers. Jezero, so blue is lower elevation, and then green is higher, and yellow is highest. So this crater from middle to the rim is about 1 kilometer of relief. Over on the left, there's a river channel that came in here where water entered, and on the right, it's a bit harder to see, but there's a river channel where water exited the crater. So we estimate that the maximum depth of a lake in here was about 300 meters. When you have a river laden with silt that enters a lake or an ocean, of course, that silt gets dropped and forms a delta. I'm getting a little bit ahead of myself. Here's the artist's rendition of that crater filled with water. It's a little bit different vantage point. So the river coming in is at the top here, and the river exiting is over at the right. So back to the story about a delta. So we have a delta over on the left side of the west side of this crater. And for scale, I don't think I mentioned the crater is 45 kilometers in diameter. And so down in the lower left is the delta. And if you imagine yourself being up in the air looking toward the delta from about where that arrow is, here's what it looks like in rendered 3D relief. We have enough stereo imagery from orbit that we can create elevation maps with a resolution of about 1 meter per pixel. So that's how we created this. And so where did Opportunity land? Where those red X's are, it shows you where Opportunity landed. I think it's about 2 kilometers from the delta, if I remember right. And so we don't know how long this lake persisted, but it could have been millions of years. And so that might have been long enough for some chemical evolution toward the chemistry of life. And so we really want to go, and if it did, it might be preserved in those sediments. So we really want to go and look at the minerals, look for organics in this delta, and bring back samples from the crater floor, from on top of the delta. And eventually, if the rover survives long enough, it will exit the crater and go and explore some even older terrain outside the crater. So actually, now if you look at this rendering in the lower right, you can see that it's pretty rough terrain. So it's rough. There are steep slopes on the margin of the delta. In the upper left, if you can make out a black ellipse, that's what we call the landing ellipse. It's about 9 by 7 kilometers. And that's essentially, we have 99% probability that the spacecraft will come down somewhere in that ellipse. And so in previous missions, we haven't had any intelligent guidance to steer to any particular place in the ellipse. But to land here, we have to have that to have a safe landing. So if you just note this crater over here and just remember that relative to where the delta is, this is our landing hazard map. So there's that crater I was talking about. This is our landing ellipse. Whoops. Of course, the delta is kind of in the upper left quadrant here. And the color coding here represents how safe or dangerous it is to land. So red is dangerous, blue is safe. And you can see that a relatively small fraction of this ellipse is actually safe. So we designed a capability for the spacecraft to use images as it descends to register those images in real time from an altitude of 3 or 4 kilometers to prior maps. So we could estimate its position with an error of about 40 meters during descent. And then on board, it could plan trajectories to reach about 700 meters of horizontal divert, because it knows in advance from this map where it's safe to land, so it can target a safe place. And that's what took place. I didn't put a video of that or an animation of that in this package, but you can easily find animations of that on the web. So I worked on part of that back in about 2006. I actually conceived the high-level structure of the vision system to do this, and then colleagues of mine spent the last 15 years developing and bringing it to full maturity. So this is a graphic of the whole landing sequence. So we've got the spacecraft up here. It's the, well, so we release what's called the cruise stage that has the solar panels and attitude control jets for cruise from Earth to Mars. We come into the atmosphere. I'm going to skip some of the details here. At some point, we release the parachute. And then we drop the heat shield. That allows us to operate a radar altimeter, actually altimeter velocimeter. So that tells us our altitude and our velocity. Then we have a camera in there that takes the pictures I was talking about. We can use those pictures to estimate where the descent system is. Tucked up inside this back shell is the rover, and above the rover is kind of a backpack that has the rockets on it, the propulsion system. So before we release that, we generate the trajectory, then we release that. We fly our lateral divert maneuver until we get down to about 20 meters above the ground. Then the propulsion system comes to a hover and lowered the rover on a set of cables, set the rover down on the ground. Then those cables were cut and the propulsion stage flew away and crashed somewhere else. So that all worked flawlessly on February 18th. It looks like we landed with an error of about 5 meters from where it targeted from 4 kilometers altitude. Here's an animation that illustrates that process. So it picks several templates in the image to correlate with a prior map, and then plans and executes this lateral trajectory I was talking about. Okay, so let's move on. Okay, so here we have the delta again, the landing ellipse, and this little blue token pin illustrates where the rover landed. These white lines are meant to just illustrate the field of view covered by the first panoramic image that we took. So if you remember the image of the rover I showed you, it had a mast with pan tilt capability with the zoom camera in there. So they built a nice zoom mosaic, and this knob over on the left side of the mosaic is this knob you see here, and then the right side of the mosaic is this part of the delta over here. This zoom is this knob over on the left side, which is this knob here, and scale bar shows 10 meters. So you can see that the delta is about 40, 50 meters tall. So that's our target. So for example, that instrument on the mast that has the laser to measure mineralogy, if we could come close to this exposed cliff edge of the delta, then we could potentially measure mineral content through time over the formation of the delta. So now what happens? Okay, so rover landed. Now I'm showing it with the white dot. I'm not part of the operations team, so I'm not involved in the day-to-day planning. I get sort of through the news a little bit like you do. But the very first look considered two possible routes. So this rougher area in the image is full of sand dunes. The rover cannot get through there. So there's a route to the north around that, a route to the south around that. I think it's actually going north. And what we want to do is get up onto the delta so that we can take samples on top of the delta. I'm not quite sure why it comes down here, but then, as I was saying, we eventually get up outside the crater, and then there's a region to the southwest with even older terrain that we'd like to go and study. So that's the rough plan for what the rover is going to do. Now, I'm trying to keep this very non-technical. I've just got a couple of slides that give a little bit of information about how this works inside. So we've got these prior maps we create from orbit with a resolution of 1 meter per pixel. So we do route planning, and then the rover has onboard perception and local path planner. So we use the stereo cameras to do 3D perception. We build an elevation map on board. The rover can't steer and drive at the same time. It doesn't have enough motor control channels. So it sets the wheels for a particular steering direction, and then it drives about 1 meter, and then it stops, and it, well, might not stop anymore. Yeah, it does stop. It turns the wheels to a new direction and drives another steering arc. So the path planner is what we call a tree-based planner now. It builds this search tree of potential paths, and then it samples positions along those paths, and every 25 centimeters, it does approximate clearance estimation. So it checks for the possibility of high centering, driving over rocks. It checks the slope, things like that. A little bit more sophisticated than we did for Spirit and Opportunity back in 2004. So essentially does this repeatedly as it crosses the terrain. And it uses something we call visual odometry, uses the cameras to track features on the terrain as it drives by them to help estimate its position as it goes. So the Ingenuity helicopter is here as a technology demonstration. It's the first time we've tried to, or anyone has tried to do heavier than air flight on another planet. So for scale, this is about 50 centimeters tall. It's a counter-rotating coaxial helicopter, so those rotors spin in opposite directions. They're about 1.2 meters in diameter. They're made of carbon fiber. They spin at about 2,400 RPM. There's a little bit more detail about it. So we've got it's a UHF radio antenna on top there, solar array. Inside this electronics box, we have a computer architecture that has a microcontroller to do all of the real-time control and state estimation. And then we do image processing like we do on the rover to do visual feature tracking to help estimate position and velocity. We do that with a cell phone processor from Qualcomm, the Snapdragon 801. That was first announced back in 2014, so that's fairly old by now. We've got 2 cameras on board. There's a down-looking black and white camera we use for navigation, and then there's a forward-looking 13 megapixel color camera that we hope to take some pretty pictures looking out over the terrain. Inside, of course, we've got rechargeable lithium-ion batteries that we charge overnight. This only has enough power to fly for about 90 seconds a day. And then it will land and recharge until the next time we try to fly. Now, it got to Mars strapped to the underside of the rover. If you've been watching the news, you might have seen that this was covered with a debris shield so that it didn't get destroyed by rocks blown up by the rockets during the landing event. And then the rover is going to drop that down on the terrain. So we have an animation here of what that's going to look like. So if we stay on the current schedule, we expect to put the helicopter down on the ground next Thursday. And then it's going to take about 10 days to do a bunch of checkouts before we're actually ready to fly. And then the primary mission for the helicopter is only 3 flights. So the first the rover is going to drive off about 50 meters away. And we'd really like to get some pictures of the helicopter in flight. So the rover will be watching the helicopter. And in the helicopter's first flight, it's only going to go up to about 3 meters altitude and hover for about 20 seconds and then come down and land. And then it's going to take about 3 days for us to downlink telemetry about how that worked and look at it and be comfortable about how it all worked. And then 3 days later, we'll try again with the second flight where we'll go up to about 5 meters altitude, try some horizontal flight. And then we want to come back and land in the same place we took off because this aircraft does not have the ability to find landing houses. We didn't have enough money to build that in. So the rover has to put it down someplace that we know there are no landing houses. And then in the third flight, it would fly further downrange, maybe 50 meters, then come back to where it started again. And the real purpose of this mission is, of course, what the rover is going to do to look for signs of life. So we really want to get the helicopter part of the mission over as quickly as we can so the rover can go and do its science. So we may do as many as 5 flights, but the baseline is to do 3. And this is just artist's conception of it, taking some images as it goes. Those are used both for navigation and for some other technology experiment purposes. See how well we can map the terrain from a helicopter, for example. So then it will go back and land where it took off from, or land again from where it took off. So that's what we hope to happen over the course of about the next 5 weeks. So this is another orbital image, or this image might actually have been taken during descent. The scale bar down here is about 20 meters. So the graphics here illustrate where we want to put the helicopter down in the smallest square is about 3 meters on the side, and what's called the airfield is 10 by 10 meters. So that's where we want the helicopter to come land again every time. And then we basically mapped out this flight zone that's 30 meters wide and 50 odd meters long that it'll do its flights in. So, and then the delta's off to the left here. So that's what's going to happen with the helicopter. Here is, I think, a little mosaic of what it looks like from the rover cameras with overlaid graphics. So the smallest quadrilateral here is where we'll put the helicopter down, and then the larger one is the 10 by 10 meter airfield, and then downrange there is where we'll do our longer flights. So that's the mission for the helicopter. Now, how will it navigate? So this is some video we took from one of our engineering development vehicles. So the navigation camera is about 130-degree field of view. For those of you who are into that kind of thing, it's a global shutter camera. It's actually a cell phone camera. And what we do is visual feature tracking to estimate displacement from frame to frame. And so together with an inertial measurement unit and the altimeter, we can estimate position and velocity. And so these little green dots represent where the software picks features in the image. And that's basically high contrast places like the corners of the stones. And then as we take off, we track those. And what you'll see is overlays of all the features as we track them. And we only track them for maybe 10 or 15 frames, and then we throw them out and we pick new ones. And over on the right, we're illustrating that we picked them in a base frame and we track them for a while in the search images, and then we start over again. And so that's the heart of the navigation system for the helicopter that runs on the cell phone processor. Okay, now this is kind of a busy slide, but it is meant to illustrate Mars sample return, and I'm going to just skip over this. So the idea for sample return is we'll send this sample retrieval lander. If things go well, we'll launch that in about 2022 or 2026, could be 2028. And it has a 4-wheeled rover all kind of folded up on top. there's a little lever that will kind of flip it over and put it on the ground in a deployed state. NASA is building this lander. Europe is building the rover. So here is a video made by the European Space Agency illustrating that rover in operation. It will drive around and find the sample tubes and use an arm on board to pick those up and stick them in a little holster on board. So we'll probably drop these sample tubes about a meter apart on the ground. So it'll go and pick them all up. It's a long story why we drop them on the ground. You can ask me about it later if you want. And once it's picked them all up, it goes back to the lander. The rover and the lander have arms. Inside that lander, there's a Mars Ascent Vehicle rocket. And we want to stick all those sample tubes in sample canister that looks like this. I don't remember the size of this, but it's probably 50 centimeters or so tall. That gets stuck in the nose of the Mars Ascent Vehicle, and then we launch that into orbit. In the meantime, the Earth Return Orbiter has arrived, and it's waiting in orbit for the MAV. There goes the MAV. So it's going to get into orbit, and then it's going to release the sample canister, and the orbiter is going to perfectly match orbit with the sample canister through magic that I'm not involved in. And it's going to ingest the sample canister. So that gold colored thing on top is, inside that is the Earth entry vehicle. So it's basically a heat shield. There's a fairly complicated mechanical system inside. So I talked about planetary protection. We're going to take that sample canister and stick it in another hermetically sealed container so no Mars bugs can get out, and then stick it inside the Earth return vehicle underneath this solar blanket, and then cruise back to Earth. When it gets close to Earth, it releases the Earth entry vehicle. The orbiter will be diverted past Earth and just go into orbit around the sun. And then the Earth entry vehicle, it doesn't even use a parachute. It just does a hard landing in the desert in Utah. And then a crew goes out and picks up the samples and takes them to a lab, and we study the samples. So if all goes well, this will be done around 2031, possibly later than that. Okay, so that's the story about Mars. Now, if Ingenuity succeeds, touch wood, we show that it's possible. What are we going to do next? We're working now to try to design a larger rotorcraft, which might be a hexcopter that could carry a larger payload of scientific instruments and access places that you just can't get to with a rover. So places that are too steep, or be able to actually cover more territory than a rover, so do longer exploration than a rover. So we're working on technology for that. And then other places that are priority to visit in the solar system extend this theme of looking for signs of life in the solar system. So we now know that there are a number of moons in the outer solar system that have liquid water oceans underneath water ice crusts. And so one of the most interesting of those is Enceladus, which is a moon of Saturn. It's about 500 kilometers in diameter, and gravitational flexing basically caused by Jupiter. This is at Saturn. So Saturn, and then Titan is a much larger moon a little bit further out. That flexes the shell of Enceladus, and it keeps the inside warm enough to keep a layer. This is not the scale. The ocean is not this thick, but it keeps a layer of liquid water. And the Cassini spacecraft observed jets of water vapor coming out of cracks in the surface near the south pole of Enceladus. And it was even able to detect, I think, some small organic molecules in those jets. And that, I think, comes from interaction between the water and the rocky, icy core of Enceladus. So we'd like to go back and study this some more, be able to take better instruments to look at the jets, maybe sample stuff that falls back to the surface near the jets. And ultimately, the goal would be to penetrate the surface so we can actually sample the water. So either drill, or these vents perhaps we could send some kind of crawling robot that would go down the vent and sample the water. So other places out there that have oceans, some of the moons of Jupiter that you see listed across the top, Titan, the moon of Saturn, and then some other smaller moons out there. So that's part of the ambitions we have for the next 10 to 20 years of solar system exploration. And with that, I'll stop. Back to you, Daryl.
Thank you very much. So let me get set up here for questions. So first question, how does the MSR launch the sample canister to meet up with the orbiter?
Well, that lander will have a rocket inside. We call the Mars Ascent Vehicle. And there's been studies of whether that should be just a solid rocket or some hybrid. I think it's a single stage. But I'm not at all involved in that, so I don't really know the details. But it does have this ascent vehicle tucked inside, and after landing, you know, the rover, we call it the fetch rover, sticks the sample tubes in this sample container that goes in the nose of the Mars Ascent Vehicle, and then that gets tilted up so that it can launch up into orbit.
Okay, so are there any plans to make a skyhook or space bolo?
Not that I'm aware of. So the idea of a skyhook, if we're talking about the same thing, there have been some ideas that maybe you could have a really, really, really long tether made out of Kevlar that would basically rotate in orbit and come down and touch the surface and be able to then swing payloads up into orbit. So I'm not aware of any work to try to prototype that.
Okay. So you asked about, here's the question you asked for. Why do you just drop the sample containers on the ground?
I think ultimately there was a concern about what happens if Perseverance dies partway through the mission with the samples still inside. Could we ever get them out? And so this is basically an insurance bet that we don't get stuck with a dead rover full of sample tubes that we can't reach. So at first blush, it seems like an odd idea, but when you looked at the big picture, weighed all the risks, this seemed like the lowest risk approach.
Okay. So what are your thoughts about the Starship reusable spacecraft designed by SpaceX? And how important will they be for future endeavors?
Well, to start, sorry?
No, there's a part two, but go ahead.
Okay, well, let me give two answers. So the reusable boosters that SpaceX has been building for going to Earth orbit, I think are very important for improving the affordability of getting to Earth orbit. When you take a hard look at what the real numbers are, I'm not sure how much money it saves, but the idea is that it saves a lot of money. You know, as far as taking people to the moon and then to Mars, there are actually 3 companies competing right now for a contract to build a rocket to take people back to the surface of the moon. So that's SpaceX, Blue Origin. They're in a consortium they call, I think, Blue Federation, and then a company called Dynetics. So SpaceX is one of those. They have kind of a unique design that they hope to take all the way to Mars. You know, I'm not really involved in the human space program, so can't tell you much more about that.
Okay. So how fast is a vehicle observer observe the route, plan a route, assess the 25 centimeters, and then actually drive. So how long does that loop take?
Well, we want the rover to drive at a peak speed of about 5 or 6 centimeters a second. So while it's driving, it will drive at 5 or 6 centimeters a second. In previous missions, we had a very slow computer. I kind of skipped over it in one of the slides, but Curiosity has a processor which is basically a PowerPC 750 from the mid-90s with a clock rate of about 130 megahertz. So, the clock rate itself is a factor of 10 or more slower than modern processors, and the architecture has a lot less computing capability, even leaving aside the clock rate difference. So it's really slow. In Perseverance, we've put a coprocessor that uses a field programmable gate array, or an FPGA, and we've implemented the vision algorithms in the FPGA. So now, instead of taking maybe a minute per meter just to do the image processing, we can do the image processing in a fraction of a second. So that lets us drive at 5 or 6 centimeters a second for about a meter at a time, and then we stop and we turn the wheels, and then we start again. And so what the average traverse velocity is, I'm not sure, but we want to be able to drive about 200 meters a day in the steady state when we're trying to go from place to place. And that compares to Curiosity, when it's doing the same level of autonomy, it can only do 10 or 15 meters a day.
Okay. So what is a simplified development process to include things like a helo and your specific part of that process, such as, do you look at capabilities first or scientific demands and so forth?
Well, missions always derive from scientific objectives. People like me also do, what's called technology push. So I'm always trying to keep in touch with the scientists to have at least a general idea of what missions they'd like to do in the next 15 to 20 years. And it needs to be 15 to 20 years because it takes that long to develop and mature this stuff. So it's a bit of guesswork when you're projecting that far in the future. But eventually you meet in the middle. I'll develop something and nurture it along, and I'll look for combinations of NASA and non-NASA money. So I've done a lot of work funded by the Defense Department over the years. And then on the mission side, some science mission will come along and realize they really need what we've been working on. And then they take it over and they mature it to flight. And like I said, that whole cycle is often 15 to 20 years.
Okay, so is there technology transfer from your work that makes its way back to industry? You say there are cell phone cameras being used on the helicopter, for example.
Well, so actually cell phones are one of the shining examples. Modern cell phone cameras use CMOS imagers, which basically succeeded CCD imagers. They're smaller, they're lower power, they're cheaper, and the core technology that enabled CMOS imagers was developed by some people at JPL, and then they left and started a company and commercialized it. And I think eventually other people developed other versions of it, and now the biggest suppliers of CMOS imagers, I think there is still one or two in the US, but Japan and like Sony and Samsung are big suppliers of those now. But Caltech made a huge amount of money in patent royalties. So things invented at JPL, the patents get owned by Caltech. Caltech made an enormous amount of money out of patenting CMOS imager technology.
Okay. So when you received your education at the U of R, did you know at the time that you wanted to have a career in the space sciences?
I had no idea. I started U of R being interested in computer science. I knew I wanted to do something that felt like it was cutting edge. I got interested in artificial intelligence. My advisors told me I'd better go to grad school for that. So I went to the University of Waterloo for a master's degree. I studied computer graphics there. Then I went to Carnegie Mellon University for a PhD and ended up studying computer vision for robots. When I graduated, I wanted to do robots for some outdoor application, and I got an offer from JPL, and that was really when I started working on space.
Okay. Given the earlier rovers far outlasted their mission life, what is life expectancy of Perseverance?
So that RTG nuclear power source should last at least 14 years. So Curiosity has the same thing. It's been operating on the surface now for going on 9 years.
Okay. How autonomous is the rover and how does it come back compared to the earlier Spirit?
How autonomous? Well, so key difference is that FPGA coprocessor I was talking about. And the main difference that makes is it lets it drive a lot faster. There isn't that much more autonomy in the sense of being able to do more independent decision making. There is a little bit, so it's actually surprisingly complicated to plan the activities of a rover on Mars because it has to keep track of a lot of things. So it has to keep track of the state of its battery. It has to keep track of all sorts of temperature measurements. It has to keep track of how much data is stored in memory. It has to be aware of where the satellites are that it uses for communication relay. A lot, and the mission every day has a lot of different activities, and these all have to be scheduled. So there's a scheduler on board that does more of that on board now than was done previously. So those are the main differences: a more intelligent onboard scheduler for the operations within each day, and then the ability to drive a lot faster.
Okay, sometimes it feels like coming from Regina is limiting, so it's cool to see people from here doing really interesting and valuable work. How did things line up for you to end up at NASA?
Well, I hope everybody feels they do interesting and valuable work no matter what they do. The way I got to where I am is, it was a long path where, like I said earlier, I didn't know I wanted to be at NASA. I wanted, to go and find leading edge computer science to do. And the way things happen with this is every opportunity you get, you have to make the most of that opportunity. And then you have to be looking forward to the next opportunity and make the most of that one. And it's basically one step at a time. You can never be sure what opportunities are going to come to you. You can have a long-term game plan and you aim yourself in the right direction, and then you make the best of how the cards fall. So, that may sound a little bit like motherhood, but I think that's basically the way it happens.
Okay. So will solar panels still be used with the new Mars rovers, or will nuclear battery power be the norm?
So for Curiosity and Perseverance, we had to use the nuclear power because to get enough solar power would have been a way too large a solar array. So we can use the solar arrays on smaller rovers. And also when we were initially designing these last two missions, we thought they might go to colder places, basically higher latitudes where there wasn't going to be as much solar energy. So it's not so much that it's cold, but higher latitudes. And so the nuclear power also lets us go to higher latitudes. But if we do more rovers at smaller scales, without going to extreme latitudes, they could be solar.
Okay. Okay. Well, thank you to our speaker, Larry Matthies. Thanks for joining us on this March evening.
It was a pleasure. Hope you all enjoyed it, and nice to virtually see you.
Likewise. Okay, so thanks everybody, and if you have comments or questions about this series, please let me know. And we hope to see you before too long with our next event.